frictional force, because the frictional force is another one of these kind of bizarre topics here. Okay, what we find here is that there are two types. Two types of friction. Okay. And what you're going to find here is that one is known as static friction versus kinetic friction. Now, what's special about this? So typically, what you're going to find about static friction is that this guy is a variable force, whereas this guy is a fairly constant force. And when we talk about it, you'll see that it makes intuitive sense. And so how do we typically write the static force, the static friction? We typically define it as F of S. And when we look at the kinetic friction, we typically symbolize it with a little k symbol. So we differentiate between these two frictions in this way here. So what I want to do here is that I want to do an imaginary demonstration here. Okay. So here's my imaginary demo. And what I'm going to do here is that I imagine that I have a surface with a block. And this is a rough surface. And we could imagine that we have this block right here. Now, what I'm going to do here, and remember, this is a rough surface. And what I'm going to do here is that I'm going to attach a spring scale. So here, what I'm doing here is that I have a spring scale. And it has a scale reading. And typically, the ones that we have in the lab, they have a little hook. Okay, so this is the spring scale. And I have this little hook here. And what I'm going to do here is that I'm going to come in and I'm going to apply a force to this thing here. So I'm going to come in here and I'm going to say, okay, now I'm going to apply a force in this direction. Okay, so this force here is equal to the pull on the spring. So the question is, what happens here? Well, when you pull on this thing, what you find here is that your initial pull does not cause the block to actually move. So I'm looking at this situation here. And if I look at this thing here, and I think I'm going to copy and paste this a couple of times just to give you a sense of what I'm talking about. So what I'm going to do here is that I'm going to copy this and I'm going to repeat this process 4 times. So I'm going to go paste. Okay, so now let's look at the situation. What I'm going to do here is that I'm only going to pull a little bit. Okay, so I'm going to pull a little bit right here with the little force. And what happens here is that because of the friction at the surface, the friction, which is opposite of what it's doing here, is like this here. Now, this is static. So what we say here is that the block remains at rest. Now, here's what happens here. If there's enough friction, I can actually pull harder. So my force has now increased. And what you're seeing here is that the block does not move, but the frictional force has increased. And what you're seeing here is that here it remains at rest. And then what you're going to find here is that there's a critical point. Okay? You're at a critical point called the breakaway. And what you're finding here is that the force now is just about to really break through the friction, but it's not moving yet. It's at that critical point. And so what you're seeing here is that you've now reached what we call maximum static friction. And still, it's at the critical point called the breakaway, but it remains at rest. And so what you're seeing here is that, check this out. This tells us here that this is a variable force. And so what I'm doing here is that if we were to draw a graph, okay, if we were to plot the frictional force versus time, what would I actually see here? What you're seeing here is that as I plot this guy, is that this frictional force is actually growing, and it doesn't grow linearly. So it continues to grow and grow and grow and grow. And then at some point, this is the point where this guy is the maximum frictional force that you can have. So no, I didn't label my axes yet. There's friction, and I know that that is time. And then what happens here is something dramatic happens. The friction, almost like a discontinuity. It's not a discontinuity. What it does here is it effectively jumps down. And then you get almost a constant here. And so what you're seeing here is that along here, you're seeing the variable nature of the force. And then when it jumps down like this, you could see that the force is fairly constant here. And what happens here is that the force decreases. So what ends up happening here is that at this point here, so if this is the critical point up here, what you're seeing here is that suddenly what you're finding here is that there's a switch from F static to F kinetic. And so there's a reduction in this force. And so suddenly what you're seeing here is that now there's a smaller kinetic friction, even though the other force may be exactly the same. And what you're seeing in this case here is that you now have acceleration, right? There's now acceleration where the block begins to slide. Okay, it begins to slide here. So what you're seeing here in this region right here, this is the region of static friction. In this region right here, you're seeing the region of kinetic friction. Now, there's, you have, I think you have good intuition about this. And what do I mean by that? By the way, I noticed that I didn't label this point here. This point right here is the so-called the breakaway point, right? That's where that discontinuity does. So let me see if I can help you with some analogy here. And you may have noticed this. Let's say that you're going to be moving a couch on, let's say, carpet, for example. That's where I really notice it myself. So what you find here is that you have an initial push with no motion. So what do? You then push harder and you still have no motion. But what you find here is that when you push even harder, then motion occurs. So that means you're at the breakaway point. But you probably realize this, that once motion starts, you can let up on the pushing. And that's telling you that there's now less push required to keep it moving here. So what I've done here is that I've essentially did what here? I've come in and I've tried to give you sort of like how we know that friction is occurring, but I haven't given you any physical picture here. So let's go to this thing here. And what I want to do here is that I have this image here. So let me share this image with you here. This is polished stainless steel at a 1/10 micron scale. In other words, when you look at the microscopic scale, it's rough. What do I mean by it's rough? Look at this thing here. If you look at this guy, you can see that there are peaks, valleys, and this is polished steel, right? You have lots of peaks and valleys here, right? Lots of peaks and valleys here. And what you're finding here is that the cause of friction is essentially how these peaks and valleys interact with each other. So friction is the interaction of the peaks. How about if I do that? The peak and valley, the interaction between peak and valley of two different materials. And what we find here is that when you really look at the detail interactions, what we find here is that the force of friction is it's really the quantum electrical interaction between molecules of two surfaces. And so what I want to do here is that I want you to have a particular image of what I want you to think about. So let's go do that. So here's my image. So I have a surface, okay? So here's my surface right here. And that's going to be, we could say that's the floor. So when I'm thinking about this thing, I want to really color these guys here. So I'm going to imagine that here's my blue surface. And then I have an object. And this object is the object that I've been using here all along, is my purple object. So when I look at these two here, what you're really seeing here is that you're looking at the relative motion between two surfaces. So in other words, I'm going to look at the motion of this guy, the blue surface going this way, and then I'm going to look at the relative motion of the purple object moving that way. So what do I mean by this? Well, when I look at the surface of smooth stainless steel, you could imagine that if I'm talking about a regular surface, now what I want here is I want the microscopic view. What's the microscopic view look like? Well, there's the blue surface. And when I'm thinking about the blue surface here, I'm having peaks and valleys, something like this here. So here's my blue surface. And now I need my violet surface. So when I'm looking at the violet surface and I'm looking at the microscopic level here, what you're seeing here, it also has peaks and valleys too. So when I go and I look at these surfaces, you're getting a picture that looks something like this here. So now imagine here, let's say that the purple is sliding. So if the purple block is sliding in this direction, right? This is the motion of purple block. What you're seeing here, as the purple block is moving, trying to move across this thing, what you're seeing here is that this blue peak right here is applying a force in that direction. And this blue peak is applying a force in that direction. And maybe this blue peak is applying a force in that direction. And what you're seeing here is that as they interact, you're essentially trying to move peaks and valleys over a different set of peaks and valleys, right? So the motion over the peaks and valleys is what we call friction. What we call friction. And what you're seeing here is that as they interact, what you can do here is that you can get what is called excitement in the molecules, which essentially causes lifting of the molecules. So what you're going to find here is that if I have static friction, and what we found here is that motion does not occur But there is a tendency to want to move. So if there's a tendency to want to move, you could see how even though we cannot detect motion, there is motion at the microscopic level where the peaks are interacting. So you could see here is that if I take this picture right here, let me see if I can grab this picture. Let's look at static friction here. So if I'm looking at static friction right here, you could see that if I'm trying to move in this direction right here, so even though my motion is zero, you could see how those blues are going to oppose those purples because there's this just microscopic motion here. And what you find here is that when you deal with kinetic friction, this clearly has, motion now occurs. So what's going on with this here is it turns out that if enough energy, and we haven't even talked about energy, right? So if enough energy is put into the system, what you find here is that there is a type of excitement, and this is where quantum mechanics excitement in the molecules that effectively lifts up and reduces interaction. Now note that what I'm really telling you right here is a white lie. Okay, it's a white lie, but there's no other way to explain it. Otherwise, we'd be talking about quantum mechanics, which is beyond the scope of this course here. So that's how I visualize friction here. So what I want to do here is that I want to go in and I want to look at a list. Okay, I want to look at a list of what's going on here. So what I'm going to do here is that I'm going to do a limited list of properties of friction. A limited list of, and here's what we know. Most of this is experimental, by the way. Okay, friction always opposes motion. Period. Look at the picture. Right? Even if I go the other direction, the peaks are going to be interacting. So it doesn't really matter. So what I'm saying here is that if I have surfaces, regardless of what the surface looks like, right? Regardless of what the surface looks like. So when I'm thinking about surfaces here, I could think about vertical walls. I could think about ceilings. It doesn't matter. If I have a block, no matter what that block is doing, right? If I have my block and it's on a surface here, if my motion is to go whatever direction I'm looking at, the frictional force is always going to oppose It's always going to oppose you, no matter what. We are always having this scenario here. So what I'd like to do here is that I want to come back in here and I want to look at the next property. What we find here is that experimentally, friction to a large extent only depends on the normal. I need to bring this down a little bit. Only depends on the normal force for low speeds and low heat transfer. Okay, so if I have low speeds and I have low heat transfer, then we can say here that the frictional force, okay, that the frictional force in this case, we could say here is that friction is proportional to the normal. So what this tells us here is that friction and the normal are equal if I have a proportionality constant. So this guy right here is a proportionality constant. And this proportionality constant is called the coefficient of friction. And it turns out that because we have two different types of static values, we have three kinds of coefficients. So mu of S, which is called the coefficient of static friction. This guy is what? It's not a constant. And then we have two constants. Maximum static friction, this guy is a constant. And mu k is also a constant. So in essence, there's really three frictional forces, if I could say it that way. And what I mean by that is that there's f of s, which is mu of s times the normal. And of course, we already said this is a variable force. Or I could have maximal static friction. And this guy is a constant. Or I can have kinetic friction times the normal, and this guy is a constant. So we have these constant and variable frictional forces here. So to give you a sense of this thing here, what people typically put down is that they put in coefficients here. Now, even though when you look at these coefficients here, check this out. Look at this guy right here. You're just seeing mu s, but what this really is that this is mu s max, because they're giving you one value. Okay. And so what you're finding here is that when you look at these tables, what you're seeing here is that they're comparing, you have to compare two different surfaces when you're talking about friction. So when talking about friction must compare two surfaces. And you could see that that's exactly what we're doing right here, right? So think about it. Look at glass on glass. You could see that once you put glass on glass, it has a large coefficient of static friction. But once I start moving glass on glass, you could see that the kinetic friction drops off. And another thing that I didn't say here, mu s max can be greater than 1. A nice example of this is rock climbing shoes. Rock climbing shoes have a particular rubber that could give you a coefficient of static friction that is higher than 1. So it's not limited to 1. You could have larger values, as you could see with copper on cast iron here. So what we did last time is we did the following thing. Here, let me get set up here. So we started talking about friction. And this is the way I could demonstrate the two types of frictions here, is that if I pulled a block with the spring scale. So if I pulled a little bit and it remained at rest, then the pulling force had to be balanced out by the frictional force. If I pulled harder, then that means that the static friction had to get larger. And there's the breakaway point. And if I pulled even harder and it's right at the verge of sliding or slipping at the breakaway point, then it suddenly switches from Fs max to Fk. So now all of a sudden, the force is greater than the frictional force that's kinetic, and so I can accelerate from rest. So what I did here is that I went in and I labeled these points 1, 2, 3, and 4, which is what I didn't do last time. So the fact is here is that you could see here is that static friction, which is this region right in here, is a variable force. Whereas if I look at kinetic friction, you're seeing a constant force. And that's the main thing right there. So now that I'm able to distinguish between the two, you're seeing that there's really two constant forces. There's the maximum static frictional force, and then there's the kinetic frictional force. But along points along the curve, you're seeing that you're seeing a variable change in the friction here. So now look what happens here. Why does this happen? From a microscopic scale viewpoint, we're seeing peaks and valleys. And it's the interaction between the peaks and the valleys that cause friction. So then we started to look at situations of the properties of friction. And we said that one property of friction is that we always know that it opposes the direction of motion, no matter what situation here we have. So a sliding block, a rolling tire, or a block, let's say, going up a vertical wall. And what we said here is that friction only depends on the normal force, but there's a big thing here. It depends, it's the low speeds and the low heat transfer. If you don't have that, it's more complicated. So we're seeing here that the frictional force is proportional to the normal force, but there's this proportionality constant, which we call the coefficient of friction. And we saw that there's 3 cases. There's static friction, which is a variable force, but there's a constant maximum for the static friction, and there's a constant kinetic friction. So the thing that we wanted to look at now here is that we want to talk about what does it mean when static friction is greater than kinetic? Okay, so the first thing that we want to look at here is that it's the static frictional force that moves the car, not kinetic energy. Okay, so let's write that. It's the static friction that moves the car, not kinetic friction. Not kinetic friction. And what this is really saying here is that the tire is at rest relative to the ground. And a lot of people find that quite surprising. In fact, they even have a word for this. This is called rolling friction. And it's more complicated than that. So when I'm thinking about a car scenario here, okay, so I have my road, and now I have my car. So you could imagine that here's the car. And when you're looking at this red car, the question is, what do we know about it? Well, we know that the tire is rotating. So when I look at the rotation of the tire, what you're seeing here is that the tire is rolling in this direction. So when it pushes off, the tire pushes in this direction. So this is the force of the tire on the ground. And then the equal and opposite force then has to be static friction, right? So just to make sure that we're clear, this force, this is the direction of the tire. And if it's the direction of the tire, you could see here that this frictional force right here, this guy here is external to the car. And because it's external to the car, this is what moves the car in the forward direction here. Now, one of the things that we should talk about is that we should talk about, what do I mean by static friction? Well, for starters here, when you look at tire tracks, what you find here is that tire tracks are not, how do I say this? Smudged, right? They're not smudged in dirt, sand, or snow. So think about this. So if I come in here and I put an image in here, look at these images. What do these images tell us? That the tire must, this implies here that the tire must be at rest relative to the ground. And you might say, no, that's really, well, think about this. If the tire is sliding, what pattern would you see here? If the tire was sliding, the pattern would be different. But that's not the case here. So what you're finding here is, in fact, cars have a anti-brake system, ABS. And what that does here, this is what happens, is that when one pushes on the brake pedal, right, to stop the car, the tires continue to roll. And that implies here that then static friction is slowing down the car. If you had kinetic friction, that would be bad. And so what we're saying here is that if cars relied, do I want to say relied? No, if cars used kinetic friction to stop cars, that means you have a sliding car, which then means since f of k is less than f of s max, then there's less stopping power, right? There's less stopping power. It goes way down, in fact, because typically kinetic friction is much smaller. So what you're finding here, here's another thing that I want to, let me make sure I'm doing what I'm talking about here. So that was 3. So let me go here. 4. What does friction not depend on? And I think this is quite surprising. Now, friction is super counterintuitive. Well, one, right? We know that the functional form is that friction is mu times the normal, right? That's what the functional form of friction is. So when I ask the question, we could see here is that friction does not depend on what? On speed, right? So you could imagine that you have a car, right? Here's a car. And let's say that this car is traveling 25 miles an hour versus a second car that's doing this. So this is a faster car, right? So when you're looking at this car here, let's say that this car is traveling 300 miles an hour. So when you're looking at how this car is moving here, the question is, would you expect both cars to have the same stopping power? Man, trying to stop a car that's moving 300 miles an hour, that's a serious issue, right? And another thing that they tell us here is two, friction does not depend on area. I mean, this is kind of a crazy thing too here. Imagine that we have a car on, no, I got a better idea. Let's imagine that we have a big truck, right? Here's a big truck with big tires. So when we're looking at this truck here, right, sort of like moving here, and when we're looking at this guy, what we're asking the question is, imagine the same truck, right, moving with some speed like this, right? So these tires are big, fat tires. Now imagine the opposite situation. Imagine that we had strong enough tires, but they were really more like bicycle tires, right? Super thin bicycle tires. But I have the same truck. So if you're looking at this scenario here, and you got to ask yourself, do the tires matter in trying to brake the car, right? These are bicycle tires on the truck. So the question is, you mean the contact of the tires with the road don't affect the stopping power of a car? You got to admit, you got to say, dude, that's crazy, right? That's absolutely crazy. The statement that it doesn't depend on speed and it doesn't depend on area, this is a huge simplification, right? We are making a huge simplification. When dealing with friction, when you do that. And if that doesn't answer your question, check out this image. So here's an image of a car. Look at this tire here. This tire is moving so fast, right? That it deforms and generates enormous amounts of heat. And as a consequence, the heat makes the tire grab the road better, and therefore it's able to accelerate better. So this statement up here, that this is what it depends on, is a really huge simplification. But we defined very clearly when we use friction. We use friction when it's equal to mu times n, when we have low speeds, so there's not very much heating, or we deal with low heat transfer, enough that it doesn't change the material. That's what we do here.